Hi. In this lecture, we're going to talk about replicator dynamics. And what we want to do is we want to talk about it in the context of learning. And the idea, and again, is pretty straightforward. What we imagine is there's some set of types out there. And these types are actions, or they're strategies. And each type has a payoff associated with it. That's how well that type is doing. When we look out in the world, we think, boy, these type 1s are doing really well. These type 7s are not doing so well. And then there's also a proportion of each type. So maybe 10% of people are type 1, and 30% of people are type 2, 6% of people are type 3, and so on. So when you think about how people learn, how do we do it? Well, we've talked about a couple things in this class. One is we've talked about how people just copy other people. And the reason you might do that is because you might think that they're doing something worthwhile. So in the standing ovation model, we just had people copying what other people do. And in our conformity models, people just copied what other people do. Well, if you copy, what's going to happen is you're going to copy in proportion to what other people are doing. Now, another thing you might do is you might hill climb. That was one of our heuristics. If you hill climb, what you're going to do is you're going to look and see which actions are paying off well. So when we think about this sort of environment, there's a whole population of people, they exist in different proportions, and they're getting different payoffs. We want some way of capturing the dynamics of that process. And so what we're going to do is we're going to introduce this model called replicator dynamics. That's one way of thinking about how the dynamic unfolds. Now, let's again suppose you were rational. So if you're rational and you look out there and you see a bunch of types, you see that there's different strategies people are playing. Strategy 1, strategy 2, and strategy 3. This one has a payoff of 5, this one has a payoff of 4, this one has a payoff of 3. You're just going to say, I'm going to choose strategy 1. I look out there and the strategy 1 people are doing the best. But that's a rational model. You could also have a more sociological model. This is a rule-based model. You could say, I'm just going to copy the next person I meet, figuring that if they're doing this, they must have chosen it for some good reason, and I'm going to pick in proportion to other people. So now if I look at strategy 1, strategy 2, strategy 3, I can say 20% of people are using strategy 1, 70% are using strategy 2, 10% are using strategy 3. I'm more likely to choose strategy 2 just because I'm more likely to bump into someone using strategy 2. So there's two ways you could think about how people might choose what to do. One would be to really do a detailed analysis of which actions seem to be paying off the best, be rational and pick that action. Or another thing you could do is you could be sort of just kind of lazy or just use a rule of thumb and say, I'm going to copy this other person because they wouldn't be doing this if it wasn't successful. When you think about replicator dynamics, what it's going to do is it's going to balance those two processes, sort of like rational process and the copying process. The question is, how do we do it? The idea is we're going to want to put a weight on each possible action. And we want that weight to include both the payoff, which is this thing pi, and the proportion, which we're calling probability of I. Well, one thing we could do is we could add those things up. So we could say the weight is just the payoff plus the proportion. Another thing we could do is we could say the weight is the product. It's the weight times the proportion. And we could do either one of these. What we're going to do is we're going to use this one, though. We're going to use the weight is going to be the probability that the strategy is being used times its payoff. Why? Well, here's why. Suppose that you had something that had a probability equal to 0. So nobody's using the strategy. Well, then there'd be no way of seeing it, and so it'd be very unlikely that you'd use it. But if you think about this model, where the weight to an action is equal to the payoff plus the probability, if the payoff is really high, even if the probability is low, people would use it. Well, again, we're thinking of a population of people sort of copying one another, learning from other people. If no one's using it, then you couldn't possibly think of it and you couldn't possibly use it. So we're not going to have any room for doing anything new. So if the probability is 0, we're just going to assume that there's no way anybody would ever think of it. So that wipes out this model. So what we're going to assume is the weight is the product then of the payoff from the strategy and its proportion. So what that means is we get this somewhat complicated procedure for figuring out how many people use the strategy in the next period, and this is going to be the replicator equation. So here's the idea. The probability that you play a strategy in period t plus 1, so the probability you play strategy I in period t plus 1, is just the ratio of its weight to the total weight of all the strategies. Because remember, the weight is just the probability somebody plays the strategy times its payoff. And on the bottom, we're just summing over the weights of all the different actions or strategies. So the probability you play something in the next period, the probability someone's of that particular type, is just going to be its relative weight. Okay, so let's do an example. We've got 3 strategies. Each one, they have payoffs 2, 4, and 5, and they exist in proportions a third, a sixth, and a half. So what we want to do is we want to figure out the weight of each of these strategies. So the weight on strategy 1 is just its proportion, which is 1/3 times its payoff, so that's 2/3. The weight for strategy 2 is its proportion, which is 1/6, times its payoff, which is 4, which is also 2/3. And the weight on strategy 3 is its proportion, which is 1/2, times its payoff, which is 5, which is going to be 5/2. So what we can do is we can put everything over 6 if we want. So this is 4 over 6, this is 4 over 6, and this is going to be 15 over 6. So if we add up the total weights, what we're going to get is we're going to get 23 over 6. So now if we want to figure out what's the proportion they're going to be using strategy 1 in the next period, in period t plus 1, that's just going to be 4/6 over 23/6, which is 4 over 23. The probability they're going to use strategy 2 is also 4 over 23 because it has the same weight, and the probability that you use strategy 3 is 15 over 6 divided by 23 over 6, which is 15 over 23. And notice if we add that up, 4 plus 4 plus 15 gives us 23 over 23. So what we do is we start out with a population that's a third strategy 1, a sixth strategy 2, a half strategy 3, and we end up with 4 23rd strategy 1, 4 23rd strategy 2, and 15 23rd strategy 3. That's how replicator dynamics works. It tells us how this population moves over time as a function of the payoffs and the proportions. So here's what we want to do. We want to apply this to games. So here's a very simple game. And we can think of this as the shake-bow game, where shaking has a higher payoff. And we can ask, how do the dynamics change? So what we're going to do is we're going to assume that there's some population of people. Some are shakers, some are bowers, and we'll see how that population learns. All right, let's get started. So let's suppose we start out with 1/2 shakers and 1/2 bowers. That's our original population. Now I want to know what's the payoff. So these are our proportions. Well, the payoff, if you're a shaker, half the time you're going to meet a shaker, and half the time you're going to meet a bower. So if you meet a shaker, you're going to get a payoff of 1. If you meet a bower, you're going to get a payoff of 0. So your payoff is 1. If you're a bower, half the time you're going to meet a shaker, you're going to get a payoff of 0. Half the time you're going to get a bower and get a payoff of 1, so your payoff is going to be 1/2. So now we just have to figure out the weight for each of these strategies. So the weight on shaking is just going to be the proportion, which is 1/2, times the payoff, which is 1, so that weight's going to be 1/2. The weight on bowing is the proportion of bowers, which is 1/2, times the payoff, which is 1, which is 1/4. So what we get is, if we want to figure out then how many shakers and bowers are going to have the next period, what's going to happen is the probability of shakers is going to equal 1/2, which is the payoff for the shakers, over the weight of the shakers and the bowers. So we're going to get that that's just 2/3, and the probability that someone's a bower is going to be 1/4 over 1/2 plus 1/4, which is 1/3. So what we see is we started out with equal numbers of shakers and bowers, and now we're moving towards more shakers, but that makes sense because shakers get a higher payoff. Now if we ran this a whole bunch of times and used replicator dynamics, and we started out with equal numbers of shakers or bowers, eventually we'd end up with all shakers. So here's an interesting thing. When we thought about, well, how do we model people? We said, well, we should model people as rational. If we thought of rational people, we'd say, well, the rational people in this model would choose 2/2. So what replicator dynamics does, it gives us another way to think about what you're going to get in a game. It says, let's assume a big population of people. And let's assume initially that there's equal numbers of each action. So there's equal number of shakers, equal numbers of bowers. And then let's just sort of let the population learn according to replicator dynamics and see what happens. And what we see is in this game, replicator dynamics would lead us to 2/2. So now if we want to say, what's our model of people? We say we have two different models. One model is rational actors. Rational actors are going to choose 2/2. Another model is people use this simple rule, this learning rule called replicator dynamics. And if they use this learning rule called replicator dynamics, then unless we start out with a whole bunch of bowers, we're probably going to also end up with everybody shaking. So that's great. It gives us another motivation for sort of figuring out why we're going to get the outcomes we're going to get. Well, now we can ask the question, though, does replicator dynamics always give us the same thing that we'd get if we thought about sort of super smart people playing the game? Well, let's see. Here's another game, and this is called the SUV compact game. So here's how it works. You can either drive an SUV or drive a compact car. If you drive an SUV, your payoff is just going to be 2, because you just drive your SUV, listen to the radio, it doesn't matter. If you drive a compact car and you run into someone who's driving an SUV, your payoff is going to be 0. And I don't mean physically run in, but I mean if you're just driving down and you see one, somebody else has the SUV, there's two things going on. One is you probably can't see around the SUV, so that's bad. And also you're going to feel a little bit unsafe, so that's also bad. But if you're driving a compact car and the other person's driving a compact car, your payoff is going to be 3 because you're both getting better gas mileage, you can see around the other car, you feel safe, everybody wins. So if you think about rational people playing this game, and you think, okay, what would you want to do? You might think, well, look, 3-3's got the higher payoff, and it's in equilibrium, because if we're both driving compacts, then we have no reason to switch. You'd think that's what you get. Well, let's see what we get from replicator dynamics. So let's start out with, again, half the people driving SUVs and half the people driving compacts. Let's figure out the weight on SUVs. Well, half the people are driving SUVs, and your payoff, if you're driving an SUV, regardless of who you meet, is 2. So the weight on SUVs is just going to be 1. What about the weight on compacts? Half the people drive compacts. Now what's their payoff? If you're driving a compact, half the time you meet someone with an SUV, so that gives you a payoff of 0. And half the time you meet someone driving a compact, and that gives you, so half the time you're going to get a payoff of 3. So that means your total payoff is going to be 3/4. So the weight on SUVs is 1. The weight on compacts is 3/4. So now if I want to ask what's the probability that someone drives an SUV in the next period, that's going to be 1 over 1 plus 3/4, which is going to be 4/7. And then if I ask what's the probability that someone drives a compact, that's going to be 3/4 over 1 plus 3/4, which is 3/7. So what we see is we're going to see a drift towards SUVs. And so what we're going to get in this game is that people drive SUVs. So here's the interesting thing. If we put replicator dynamics on this game, we don't get 3-3 as an outcome. We're more likely to get 2-2 as an outcome. And what's going to happen is evolution leads us to something that's suboptimal. So now I've learned something interesting, that these replicator dynamics, this evolution of strategies, leads us not to the optimal thing, which is 3-3, but leads us to 2-2. There's actually a book written on this called High and Mighty by Keith Bradshaw, where he talks about why is it that people drive these big SUVs if it doesn't make sense. Bradshaw makes an argument that it's really been sort of the evolution of choices that have caused us to all be driving SUVs when we'd be collectively better off if we were driving the compacts. And as evidenced by this picture here, you can see that in the little car, you're sort of frightened by the big car and you can't see around it. And so as a result, the dynamics has led us towards big cars, even though we'd collectively be better off if we were all driving smaller cars. All right, so what have we learned in this lecture? We've learned that one way to think about what people decide to do is to construct a model based on replicator dynamics. And what replicator dynamics do is they capture 2 fundamental social processes. One is the fact that people are fairly rational. We take optimal actions. Another thing that people tend to do is we tend to copy other people. And so if we write down a model where people do both, where we sort of try and do the thing that's best, but also copy other people, or to think of combining those, we copy other people who are doing well, what we see is that's a way to sort of think about where a population of people might go. Now we saw in some cases, like the shake-bow game, that that's going to lead us to make the optimal choice. But then we saw in other games, like the SUV compact car game, that in fact it didn't. The replicator dynamics led us to choose something that was safer, the SUV, but not the thing that we'd choose if we were rational, all sat back and said, okay, what's the best choice here? So replicator dynamics, really interesting way to model learning and give us sort of surprising insights in some games about what's likely to happen. Different insights than we get if we assume people were quote unquote rational. All right, thanks.